tangent vectors. So that is in fact where we left off. So what we've found so far, let me just summarize that the metric has a few fundamental properties. The dl squared itself in arbitrary coordinates is given by, has the meaning, is the distance between x and x plus dx. And so you can integrate this guy to get the path length and then we also discovered there's a different representation using affine parametrization. This will show up again when we start talking about geodesics. Geodesics in this context just means what is the path that will give you the shortest length between 2 points. Right? So in flat space it's very easy. I'll just draw a straight line. We all intuitively know the straight line is the shortest path. But then I'll turn it around and ask you, how do you know? Right? How do you show in a precise way that in fact it is the shortest path? And this will in fact connect us to the other topic that we're supposed to cover this semester, which is that of the calculus of variation. But anyway, one thing at a time. Right? So we will see that in due course. So this is affine parametrization. And then we saw measurements of angles. Okay, how do you do that? So you take Gij angles and lengths and angles. So this object is the square of the length of the vector. So for example, Gij VIWJ divided by VW. V here is just the square root of this guy, so I won't write it out explicitly. This you can interpret as the cosine of the angle between the V and the V. So these are tangent vectors. V, so the metric really has these fundamental geometric qualities, which is why I keep emphasizing. Right? If you want to do calculus in a arbitrary space, doesn't necessarily have to be curved, but including curved spaces, the key object that you need to know is the metric. And as we will step through over the next couple of weeks, once you know the metric, everything else will follow. At least follow after some calculations. So we have already seen the inverse metric. I want to make a few remarks about how it relates to our discussion of a general tensor. Right? So the inverse metric can be defined, in fact it's usually defined, as the name suggests, Gjk is defined to be like a matrix multiplication in such a way that this is the inverse of this. Right? So this is basically G inverse Ij, and then G, J, K. If you write it as a matrix multiplication, so it's the IK component of multiplying the G inverse to G. Well, what is this supposed to do? This is really the inverse. It's supposed to give me the identity. Identity in index notation is the connected outcome. So I'll stick to this notation with upper indices and lower indices. And in fact, in this case, it's very important. So this is basically the definition. And that's usually the starting point. On the other hand, we've already mentioned the fact that if your indices are upstairs, that means it has to transform in an opposite way. The indices upstairs have to transform oppositely from the indices downstairs. So, for example, in your homework, you will work out Gij in Cartesian coordinate, in spherical coordinates. How do you get this guy? Remember, how do you get what from one coordinate system to the other? These are the R theta phi system indices. And if you start from the Cartesian inverse metric, then you have to contract the X indices with the X indices, so these are the X indices. And then you have to compute basically this guy, I, C, J, where C are the spherical coordinates. Okay, so but in other words, first you have to figure out what are these Jacobians. And then you have to do this contraction. And you should find the inverse metric. So this is true if this is a tensor. Okay? But on the other hand, you already know what this guy is. For example, in spherical coordinates, you know that it is purely diagonal, so it's 1 r squared sine theta squared. So in other words, you can actually, through this definition, easily find the inverse of this guy. I won't do it because the answer is in your homework. But basically, just take the reciprocal of the diagonals. But if it's consistent as a tensor, you better get the same answer. In other words, take the inverse of this, should give you the same answer through this more elaborate calculation. And that's why I make you do it in the homework. Just to check that at least in this simple case, relatively simple case, you do in fact see that you get exactly the same result. Now, camera is not running on the battery, so I charged it. Okay, let's see how long it lasts. So why is that so? It comes down to this property here. It's very crucial. So the fact that I can define the inverse metric as the matrix inverse of the metric, and at the same time guarantee that it transforms properly as an upper index object, is actually because of the invariance of this. So in your homework, so if it were inconsistent, then I would discover that upon making a coordinate transformation of these two guys, I may not get back a Kronecker delta anymore. So this is one thing I want to emphasize. So that's why this is another homework problem. All the important things you will discover in the homework. Okay. I will tell you the basics in class, but I personally believe very strongly that you should discover for yourself important things in the homework. So you will discover that the Kronecker delta with one up and one down index is in fact a coordinate invariant. In other words, the identity. You can think of this as the identity operator. Why do I say that? Because if I if I contract this with any tensor, rank 1 tensor, it will give me back the same rank 1, I should say vector, right? If I contract it with any rank 1 vector, it will give me back the same thing. And this is true in any coordinate system. So you expect that, so this is the identity in all coordinate systems. But you will discover that you can do this explicitly, right? So Kronecker Ij in, say, the C coordinate system should be related to Kronecker AB in the X coordinate system, but now you have to contract. I'm giving too much away already, anyway. As I said before, have I said this before in this class? If I give away too much, if I tell you the answer to your homework in class, you should get very angry with me. Okay, you should be extremely pissed off. You should be offended. These days people like to be offended, right? So of all things, you should be offended when your professor tells you the answer in class, right? It's insulting your intelligence, and so you should throw tomatoes at me and maybe even walk out of the class in rage. Right? You're so angry with this guy that you just walk out. You know. That's completely appropriate. Anyway, that's not serious, right? I'm just provocating. But anyway, you should look it up for yourself and you discover because that is invariant under all coordinate systems. That's why this definition makes sense. Because if I transform these two indices and I transform these two indices from some coordinate system X to some other coordinate system C, the right-hand side will always make sense. And that's why this definition makes sense. And so that's why the inverse metric has upper indices. Right? So this is something that is worth emphasizing. In case you might wonder, how do you know it's a consistent definition, right? In math, we always start from a bunch of definitions, and then the rest is just logic. But of course, you have to make sure that the definitions that you begin with in the first place make sense. Right? If you come up with some gibberish assumptions from the outset, then of course the logic is not going to help you. You're just going to run into contradiction after contradiction. Any questions for me so far? The next thing about the metric is that it has a job, a very special job of moving indices on the tensors. So I keep saying there are two types of indices, one up, one down. And actually we've already seen it in the bracket form, but I think from the practical point of view, it's good to define it again. So for example, let's begin with the rank 1 case. Vi has an upper index, but I can relate it to the lower index object through the inverse metric. So I can always just write Gij upstairs and contract the j's here, and that is in fact the definition of what it means to have an upper index object transformed from a lower index object. And likewise, if I want the lower index object I can start with the upper index guy, and I'll just contract with the metric, and I'll get from upper to lower, right? So this is exactly analogous to what I said earlier about the bras and the cats. Although that's not how I like to think about these guys, right? It's more pragmatic and actually computationally much more relevant to just do it at this level. But remember, this is related to this fact that if you lower if you contract the infinitesimal displacements with the metric, then you get the partial derivatives, okay, and vice versa. I won't do the other one, but it's basically related to each other, right? By multiplying by the inverse. And likewise for any rank tensor. So for example, if I Ti1, and then let's say in the middle I have L, and then the rest In. And I can get from here, let's call it Ik minus 1. This is Ik plus 1. So this is Ik minus 1, and then suddenly I have an M here. So all I want to show you is that I can move this index from lower position to upper position simply by contraction with G and L, the inverse metric. And likewise, if I want to go from up to down, then let me do it here. This is in fact G L M T I1 to Ik minus 1 M Ik plus 1 over In. Exactly as you do for the rank 1 guy, because you deal with this raising and lowering per index by index. Right? So once you know how to do it for the rank 1 guy, you know how to do it for higher ranks. Why? Right? So why do we move indices in this way? And again, it comes down to the fundamental definition for what a tensor is. Remember, I don't have to worry about what the meanings of these guys are. All I have to worry is about how these indices transform under coordinate transformations. So all I have to worry about is this definition consistent with the fundamental definition of what a tensor is? Right? So remember, if I go from V, let's in fact check. So that's in fact check it. That's the most pragmatic. So let me write it down in words first. So let's check that such raising and lowering operations do indeed produce a tensor. Okay. So for example, let's look at the first line. So we have Gij, and let's start with the let's start in the C coordinate system. Actually, it doesn't matter, right? So let's start in the C coordinate system, and I contract it with Vj downstairs in the C coordinate system. So now I'm going to convert it into the X coordinate system. Okay, and so what's going to happen is, remember, these are C indices. So this is I, this is J. So I'll have a Ci, Cj, and then now I have X, A, XB, and then G, A prime, B prime. Remember now I have to put a prime just to remind myself that I'm now in a different coordinate system. What's the coordinate system? It's the one where I replace C with X. Okay? And then I have to do the same for V. Vj, remember this is a C index, so I have dCj zeta. Sorry, I just wrote zeta. C needs a bit more wiggles. Cj, and then this will be dxc, dc prime. And then this is C replaced with the definition in terms of x. Okay? So again, starting from the left-hand side in the C coordinate system, now I'm transforming things into the X coordinate system. What I want to notice is the following. What I highlight is the following. Is have a J index and a J index contracted with each other. Is a scalar. Okay? That's the thing I want to highlight. How do I see that? There's a J index here and a J index here. So let's see what happens then. So let's in fact put them together, bracket them together so that I can highlight what is going on there. So I've done nothing but just move this thing over here. Otherwise, it's exactly the same thing. Only to highlight that this is contracted with this. So what is that? Well, this is nothing but a chain root. So let's write it out explicitly. dCj, dxb, dxc, dCj. This is nothing but a chain root. And so this gives you what? This gives you dxc, dxb. Well, X makes a good coordinate system. What is a good coordinate system? A good coordinate system is just a set of parameterizations in more than one dimension. If there's only one dimension, it's always a good coordinate system. You can use whatever you want, right? But two or higher, you must make sure for a good coordinate system to exist that each variable can be independently varied without varying the other coordinates, right? So it doesn't matter whether they're orthogonal or not. That's not the issue. The issue is whether can you vary one coordinate without varying the other coordinates. So why am I saying this? Because that's what's happening here. If these guys are truly independent, then when I vary one of them only, then the only guy that I'll get is when I differentiate dxb. The only non-zero guy that I get is when I differentiate dxb, dxb. That's one. If c is not equal to b, it is equal to 0. So what is that object? This is nothing but a Kronecker delta, Kronecker CB. Okay. And that means that this is just Kronecker CB, which in turn, in fact, let me emphasize it here. So dc I dxa, and then I want to emphasize that the BC indices are here. So let me write it down and emphasize GA prime B prime. I will suppress the arguments here. So now I want to emphasize this aspect. BC prime. So that means this becomes GA prime B prime C B prime. Okay, because this summation over B and over C is 0 unless C equals to B, which means I should be able to just set B equals to C right away and sum over B, which is exactly what's happening here. And so let me write down the Jacobian first, And then let me emphasize again, what we're discovering here is what I asserted earlier, which is that repeated indices, one upstairs, one downstairs, transforms like a scalar, right? Doesn't matter how complicated your tensor is. If I have I, and then I have another one, let's say P and then Q, doesn't matter how complicated your tensor is. If you have two or a pair of repeated index, one up, one down, this is a scalar. Transforms as a scalar. What does it mean? It means that if I start from the C coordinate system as we did here, then by the time I get to the x coordinate system, all I have to do is just erase this guy, put in another pair of dummy indices, but now in the new coordinate system. So if this is x, so actually let me stick to what we did here. C. By the time you're done transforming, this will become T. I don't care about the other indices for now. It will be A prime. And then it will be Q, A prime. And now it will be X. Okay. So that's what it means by scalar. It looks basically the same, takes the same form. It's replaced the old ones by the new ones. Otherwise, there's no Jacobian. Okay? No Jacobian. That's another way to say as a scalar. There's no Jacobian. But what we do have Jacobian for, we notice, is the free index here. Okay? We started from what? We started from Gij upstairs contracted with Vj downstairs. So there's one free index I. Okay? And after doing the coordinate transformation, number one, we found the repeated index, one up, one down, to transform as a scalar. But then the free index does in fact transform as an upper index object. So what you see is what I just asserted before we started, which is this guy here. That because one up, one down always gives you a scalar, and because the metric is guaranteed to be a tensor. So when you use the metric to raise and lower the index, the repeated index is guaranteed to be a scalar, whereas the free index is guaranteed to transform as a tensor. That's why when you do this contraction, you are guaranteed to get an upper index tensor from a lower index one. Right? So this used to be lower index. Now you're guaranteed, after contraction with the inverse metric, to get an upper index tensor. And likewise, you will discover exactly the same thing. So I won't go through that calculation. I'll write down the transformation rule. Likewise, you will discover exactly the same thing that will happen when you examine contraction of an upper index tensor with the metric so that you can lower this index, right? So what you discover is that if you look at this guy in the new, these are the C system. If you go to the X system, then what you will discover is remember, the repeated index is always a scalar. And the free index will transform appropriately as a tensorial index. So again, this guarantees. So the reason why that we use a metric is because, well, firstly, it's always there, right? So whenever you're dealing with differential geometry of curved or flat space-time, or flat space, curve or flat space, the metric is always there. It's a given. It's a given, and so it's always available for your use. And that's what, and the fact that it has two indices also means that you can always use it to contract it with one index to give you one index. And because it's a tensor, any questions for me regarding what we talked about so far? Yeah, so after the break, we're gonna talk about why this is a volume in the first place. No questions? Yes?
What do you mean g of x with a hat?
It's the matrix representation of this guy, right? So this is the metric. If you view it as a matrix, I is the row number and j is the column number, right? So all I'm doing is I'm suppressing the indices so that I can now view it as a matrix, square matrix, real d by d square matrix. Why? Because I want to view the transformation. Okay, anyway, so I have only a limited range according to my phone from here to here. Let me make a mark, okay? Any questions for me? Everyone is so quiet.
Even if I were to take the filler of the whiteboard.
Sure.
Thank you.
You want me to stop erasing? Or?
Yeah, it's okay. I've
Okay.
already taken
Okay.
the filler. Just
Okay.
asking if you
Yeah.
don't want to.
Yeah.
You don't want to
No,
continue
it's
the
okay.
delete.
It's okay. Okay, so, yeah, like I said, I need to make a mark, but I think I cannot exceed this line, and then over here, this line. This guy, this guy. Okay, so in fact, I think for one of your presentations, which I have to decide soon, so over the weekend, I'm going to post presentation problems. How many people do we have? 9 people. Yeah, so I think it will be a good idea. You can form maybe 3 groups, 3 people to each group. And so make some friends and form a group of 3. And I'm going to cook up some problems, including the one that I'm staring at right now, which is the spherical coordinate system in arbitrary dimensions. And what you guys have to do is, over the next couple of weeks, you will solve the problem, and then at the designated day, hopefully on a Friday, right? Because Friday we have more time. The groups will come up one after another, and you will tell us about the solution to whatever the problem is that you have solved. So this is in lieu of the midterm, right? So I don't like exams myself. It's very stressful, and I don't see the point of stressing yourself out. What's important is that you push yourself to acquire the knowledge and acquire the skills, right? So if you can solve the problems that I give you, the purpose is served. It doesn't matter whether you do it in a context of exam or you come up and present, right? To me, at least, it's exactly the same thing. And furthermore, presentation skills are also very important, right? You should be able to have the skills to come up to an audience and be able to explain your ideas clearly and coherently. So that's also an important skill. Anyway, so watch out for that. Okay, I'm going to post the problems on the web, on the course web page, hopefully by the weekend. Okay, so the next thing I want to talk about has to do with the topic of symmetries. So So I don't know whether this is an Arfken. So if you took the course with someone else, it would be taught with Arfken, the textbook by Arfken. I forgot whether he talks about it, but I think as physicists, there's the topic of symmetry and the study of symmetries cannot be overemphasized. Right? Physics, surely at the fundamental level, is intimately tied to the study of symmetry. So, for example, all the fundamental laws of nature are rotationally invariant. And this statement alone is responsible for many, many features of, for example, quantum mechanics, where you spend many, many weeks in quantum mechanics learning something called angular momentum. What is that? That actually is nothing but the study of rotational symmetry, but realized in a quantum mechanical setting, quantum mechanical system. So it cannot be overemphasized that the study and the understanding of symmetry, things like rotational symmetry, spatial translation symmetry, space-time translation symmetry, Lorentz boosts, and so forth. There are all kinds of very fundamental space and time related symmetries that are very, very fundamental to physics. So what we're going to do is we're going to study it in the context of general curved space. And then I'm not sure we'll have the time to do it in space-time, but maybe towards the end of the semester, I'll see how much time I'll have. So let's see how far we can go, at least for the rest of the hour, right? No, I don't have a clock. 11:33. Okay, so in the context of differential geometry, symmetries are otherwise called isometries. But for me, I'm just going to use them interchangeably. So I prefer to use the word symmetry. I'm one person who does not like jargon. Mathematicians like to be very precise about what they're talking about, which is of course great. Right? But as a result of that, they, at every step of the way, they try to define new jargon every step of the way. By the time you're done, you have no idea what you're talking about because you forgot where you began. So that's why I find the learning of math very difficult because it's like biology. You have to remember all the jargon. Anyway, so what we're going to do in the context of curved space, although curvature itself is not super critical here, but in a general space, is to study the symmetry in an infinitesimal way. So what I'm going to do is I'm going to displace if I'm at the current location, I'm going to now go to a slightly different position, which I'm going to call x prime, new position. And these two positions are going to be only very, very slightly displaced. C of x prime. Before I go there, let me just explain a little bit about where I'm going. So let me give two simple examples. So I say before continuing. I'm going to study symmetries through arbitrary but infinitesimal displacement. Infinitesimal displacement. But why am I doing this? So, two examples. So, example one is translation symmetry. Space translation symmetry. This is very intuitive, so let me just say what I mean. It can be in arbitrary dimensions. Let me just call this coordinate system X. And then what I'm going to do is I'm going to displace, physically displace everybody by a constant vector. Okay? And what happens is that I'm going to assume that I am in flat space. Okay? So this is a constant. And because I'm in flat space, I know exactly what's going to happen. In this coordinate system, my metric, let me be careful not to exceed this line, right? Can I see myself even on my phone? Yes, I can. Gij in the Cartesian system is just Kronecker Ij. Okay? Because this is Pythagoras theorem. dl squared is d1, dx1 squared plus dx2 squared, and so on. It's just Pythagoras theorem. But if I'm just displacing, okay, this is in fact dl squared is just dx squared. If I'm just displacing by a constant vector, and I'm in flat space, well, intuition tells you it should not matter whether I'm standing over here. Now I'm not in my phone. It doesn't matter whether I'm over here or whether I'm over here. And particularly if I do an experiment over here, as long as my experiment is exactly the same, then it doesn't matter whether I do it over here or whether I do it over here. It should be exactly the same thing. And that is the statement of spatial translation symmetry. What you do here, the outcome should be exactly the same as you do over there. So if the metric looks like that, if you are in this coordinate system, and all I'm doing is displacing over here by a constant vector, space is not any different, whether you're here or over here. Therefore, you can immediately infer that the metric had better be exactly the same form, dx prime squared, except that x here is not the same as x prime here. X and x prime are related through a displacement, but otherwise the form of the metric is the same. Why? Why is it the same? Because, as I said, the way you measure the length over here and the way you measure the length over here is exactly the same. It gives you the same kind of result. If you displace by dx or you displace by dx prime, and dx and dx prime are the same units of displacement, then the length is exactly the same. Right? That's what it means by symmetry. So that's one example. The second example is slightly less, slightly more complicated, but I think equally intuitive. Right? So let's say you study the surface of a sphere. So we remember that in three-dimensional space, we have written down the metric dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So you can easily write down the metric on the sphere let's say I let r equals to capital R. Okay, why is it easy to find the metric? Because the metric is simply the metric in space, but now you specialize your constant radius, since I'm looking at the surface with a constant radius capital R. So dr has no displacement. I'm not displacing in r, so therefore this term goes away. And all the little r become capital R. So therefore it's just capital R squared d theta squared plus sine theta squared d phi squared. Why am I talking about this? Because now I want to talk about rotation symmetry. Rotation symmetry. What is rotation symmetry? This sphere, as long as it's completely featureless, is rotationally invariant. So what it means is that unless I put some dots on it, right? I put a flag on it, whatever. If I have nothing on it, there's no way I can distinguish between different points. I can rotate it, and it will look exactly the same. Okay? That's what it means to be rotationally invariant in this case. Once after rotation, I cannot distinguish the before and the after, just like exactly here. If I put blinds on you, and I displace you from here to here, and then I take off your blinds, you will not be able to tell that I have moved you, right? Let's say I put you to sleep, and then I pick you up, and I put you here, and then you wake up. You cannot tell any difference as long as it's completely featureless. You don't put landmarks around you, then you can tell. But same thing here. So why am I saying this? If you know that if you choose a coordinate system for a particular coordinate system, you have this metric r squared d theta squared plus sine theta squared d phi squared. Remember, this is a coordinate system, which means that for a given coordinate system, there is a north pole. Okay? And given a north pole, this is the metric. But remember, this is a human construct, right? I put an artificial north pole here, and because of that, I can write down the metric. It's not an intrinsic feature of this sphere. Because I had to do calculations, so I had to define a north pole. So nothing is going to prevent me from saying, let me rotate this sphere from north pole here to say north pole here, and then call it n prime. Right? Anyone can come along and say, I don't like your north pole, I'm going to rotate it, and I'm going to get a new north pole. What is now the metric? I don't have to think. The new metric is that if this is the theta and phi, right? This is the theta and phi with respect to the old north pole. Then all I have to do is I now have to define the new equator, the new latitude lines, new longitude lines, and so on. But the radius is the same. But I don't have to think. It's just going to be the same form of the spherical coordinate metric, except now I need to give a different name to theta, a different name to phi. So I just put a prime on it, right? Otherwise, exactly the same thing. It's just that these thetas and phi's are defined with respect to the new north pole. Okay? This was with respect to the old north pole. But otherwise, the form of the metric remains the same. Because this three dots means because the underlying space is rotationally invariant. You cannot distinguish the sphere before and after rotation. Can't. There's no distinguishing feature. Right? If it was oblate, right? So how do you break this symmetry or squeeze the sphere a little bit? Then it will start to matter, right? Because then there's a fatter axis and there's a thinner axis. Then you can tell, oh, I rotated. Yeah, you rotated because now the fatter side is like that, or it used to be like that, right? But if you don't do that, if you don't break the symmetry, if you remain exactly perfectly spherical, no way to tell. Just like here, right? Unless you do something special to space, you squeeze space in a particular way, then I can tell there's a preferred direction, for example. Then if I rotate, if I translate space, then maybe not preferred direction, but preferred slicing, then the slicing might change. Then I can tell, oh, somebody touched my space. So the point is that the metric takes the same form before and after the symmetry transformation that I'm interested in, because of the underlying special invariances obeyed by my symmetry, obeyed by my spaces. And I'm going to use this two observations as simple motivation for defining in the more general case, for defining what an isometry or symmetry means. So that's what I'm going to do. So we have a symmetry if when I go from x to x of c, then I get Gij x, of course, is transformed from the C system. But it would if you transform this, if it turns out to be formed invariant, this turns out to be formed invariant. What that means is the following, that Gij can be obtained from Gi prime J prime just by literally component for component and coordinate for coordinate, replacing C with X. Okay, that's exactly what's happening here, right? I take theta, I don't have to put a prime, I can call it alpha if I want. But as long as I identify theta phi with theta prime phi prime, then you see I don't have to think. Immediately I can just write down term for term. This will become theta prime squared. This will become sine theta prime squared. This will become d phi prime squared. Same thing here. Dx squared. Just replace x with x prime. Okay, and I'll get from this metric to the translated metric because it's the same. Okay, so this is my definition of what a symmetry is in the differential geometry language. I hope, yes, okay, and I'm still in the form. I don't have to check my time. If you plug this definition into your metric, then in fact it's just calculus. You can just compute what it would do to your metric components as well as actually in my notes I did it the other way around. I call this x prime and I call this x. Okay. And so, and then what's going to happen is that you can plug it in and you will discover that the following. You will discover that you will transform this. This is calculus, okay? and a bit of Taylor expansion. And I will do it the next time. But you'll get the following. You get Gi prime J prime of x replaced with x prime. So literally component for component in the coordinates. X1 is replaced with x prime 1 and so on. And then this will be dx prime I, dx prime j, plus, remember this is very small, so I just want to keep it to first order. What does the first order term look like? C A prime partial A prime, Gi prime J prime, plus yes, it's a plus. Partial I prime, C A prime, J prime, A prime, and then plus these two indices swap. Partial J prime, C A prime, Gi prime, A prime. then dx prime I, dx prime j, and then plus, let me just say order c squared. And by that I just mean the higher terms are quadratic in C and higher. Okay? So to first order in C, this is what it looks like. If you just plug this definition into this guy. Okay? And so what did I just mention about what the definition of a metric is, of an isometry is? A symmetry preserves the form of the metric. So what it means is that if there is a symmetry, so i.e., if there's a symmetry, then we expect what? We expect that Gij of x will be transformed into Gi prime J prime, component for component, except that now x is going to be replaced with x prime, which, by the way, is exactly the first term. That's exactly what's happening. But then there are corrections. There are corrections to this answer coming from C, which is to allow us to generate new coordinate transformations through this infinitesimal displacement. What that means is that if we want a symmetry, we want this term to be zero. Right? We want the higher terms to be zero as well. But certainly a necessary condition that you need at least the first term to be zero. So if I package these three terms in the math literature, they write it with the script L with respect to C acting on G with subscript Ij. This is called the Lie. These three terms together is called the Lie derivative. It's just jargon, but in this case I should mention it because it's a standard definition for what it is. Lie derivative of the metric along C. Okay. So C, you can think of it as a vector, right? It's an infinitesimal displacement. It's a tangent vector. And so you're taking the Lie derivative of the metric along this vector field. You're generating its corresponding small coordinate transformation. But if it's a symmetry, this better be zero. In other words, this guy, again, this symbol means those three terms. In other words, the Lie derivative needs to be zero. Okay? So later on, after you learn the covariant derivative, you will realize you will be able to package this form in a tensor-looking equation. Because this doesn't look like a tensor, which I'll explain a little bit next week. But it will turn out that these three terms altogether can be packaged in a more covariant looking form like that. So grad ICJ plus grad JCI. And now these two terms are both tensors, is zero. So it's called Killing's equation. Okay. So in other words, whenever that is a symmetry generated by C, then the C is called a Killing vector, and it must satisfy Killing's equation. So C is a Killing vector. I think it's a name. Nobody is getting killed here. Okay? No, nobody's dying. It's just somebody's name, if I'm not mistaken. Any questions for me?